Hello everyone, today we are going to design Tinder. Tinder is an online dating application that allows users to anonymously swipe to like or dislike other profiles based on their pictures, a small bio, and other common interests. It uses geosocial networking, which means that it shows profiles of the users to other users within a certain distance from them. Once two users are matched, that is, they'll both like each other, Tinder actually enable them to exchange messages with each other. Just to throw some numbers, Tinder reported to have more than 50 million users 5 years ago, with 1.6 million swipes per day. So you can imagine now, in 2020, the number of active users and the number of swipes in Tinder application must have grown a lot. These are crazy huge numbers for any online dating app. So when an interviewer asks you to design an online dating application like Tinder, the very first thing that you will do is that you will discuss all the functional and non-functional requirements with your interviewer. So now let's discuss them. The very first requirement is the user need to have an account to use Tinder application. Need an account. So the user can use his or her Google or Facebook account to log in to Tinder application, which means we are using external identity provider like Facebook or Google here. The second functional requirement is the user can upload at most 5 pictures. The third functional requirement is the user will be provided with the profiles of nearby users based on certain criteria. So those criteria, which we can easily say as search criteria, they include number 1, the distance from the user. So the user can specify that he would like to see the profiles of all the other users which are within a certain distance, let's say 50 miles from the user. Gender, male or female, and sex orientation. The third is the age range. So the user can specify that he only would like to see the profile of other users who are between, let's say, 20 years to 30 years or from 30 to 40 years, etc. The user can also specify race, whether he's only looking for people from a certain race. The user can also specify different interests and activities. For example, user can specify that he likes to watch movies, so he prefers other people who also likes watching movies. Or the user can specify that he likes to do cycling and he would prefer other people who likes to cycle. Or the user can also specify he likes pets and he also prefers someone who likes pets, etc. The fourth requirement is the user can swipe either right or left to like or dislike other profiles. The fifth functional requirement is that the profiles that we have shown to a user should not be shown to him again. It would be a very bad user experience if you see some profile, you either like or dislike it by swiping right or left, and then after some time you see again the same profile again. So in this case, we have to make sure that in the Tinder application, we are not showing the same profiles which the user has already seen again and again. Of course, as a human, we usually tend to forget things, especially if someone is using Tinder app and he is on average looking at 100 profiles. I would say even after looking 100 profiles, he may forget what profile he saw 100 profiles before. And in that case, we can show the profile again. But right now, let's just assume that we are not going to show the profile to the user which we have shown to the user in the last 3 months. And we are assuming right now that for this to happen, the user is actually actively coming to Tinder and he is looking at on average 100 profiles every day. The sixth functional requirement is when the two users are matched. Match means that when both the users like each other profile, then Tinder will send a notification to both the users that both users have liked each other, and if you guys want, you can initiate messages between each other. The seventh functional requirement is, of course, again, analytics and monitoring. And this is very important, and you guys need to know that when we work in distributed systems and services, we always have analytics and monitoring. You cannot ship any feature, any product without this. And that is why in all my functional requirements, I do mention about analytics and monitoring. Now the 8th functional requirement, which is an extended functional requirement, is the users can also do video and voice chat, etc. Now let's discuss the non-functional requirements. As we have discussed before, the non-functional requirements are those requirements which does not deals directly with the functionality of the service, but they deals with the experience that the user will get while he is dealing with that service. So the very first non-functional requirement is the service needs to be highly available. And what does it mean is that the service should be able to tolerate small faults. So let's say if a node goes down or if machine goes down, some part of the service goes down, then only a small portion of the users should be affected and only for a very small period of time. The service as a whole should be available all the time for most users, and that is what we mean by highly available. In the industry, when we talk about highly availability of a service, we do provide some SLAs like the service has 99.99% or 99.999% uptime. The second non-functional requirement is the service needs to be highly scalable. What it means that with the increasing load on the service, as the number of users increases, the service should be able to scale as well. And so the overall performance and experience that the users are getting from the service should not degrade over time. The third non-functional requirement is also related to the second non-functional requirement, and it is that the users should get a real-time experience while they are swiping left or right profiles of other users. So they should be able to retrieve other users' profile very fast. And so the loading of profiles and showing it to the users should be done with minimal latency. The fourth non-functional requirement is the profiles should be durable. It will be a very bad user experience if a user log into Tinder application and find that all his images and all his bio has been gone. The fifth non-functional requirement is about consistency. I'm not going to discuss right now what would be the consistency requirement, whether it will be eventual consistency or strong consistency. I will let you decide what you think. What would be the consistency model for the Tinder application? Please let me know in the comments below. What do you think? Whether the Tinder application will be using strong consistency or eventual consistency. Now let's discuss the different APIs that are provided by the Tinder service. The first set of APIs are related to the user log on and log off. For that, we would be redirecting the request to the external identity providers like Facebook or Google. When you register your account with Tinder, then Tinder validates your account by sending a code to the phone number that you register with the Tinder application by SMS. In order to validate the account, you need to provide that code to the Tinder application that you have received from the Tinder service via SMS. We have already discussed those APIs in our previous video on designing WhatsApp service, so you should go and check that video here. There are two sets of APIs that the Tinder service exposed to the user. One is for updating the user profile information like the user bio of user interest and activities, etc. And the second API is to upload different pictures that the user can upload to Tinder service. And as you can see, these APIs take user token as input. The user token is a JWT token. JWT stands for JSON Web Token. And then of course, the update profile API takes a profile infrastructure, and the upload picture takes the image path and the image infrastructure. There is another API that Tinder provides through which the user can update his or her search preferences. This API takes user token as input and the search preferences. And the search preferences include the distance from the user within which the user wants other profiles to be shown, the age ranges that he is interested, the gender orientation he is interested, and other interests and activities or hobbies that he is interested. Now there will be another API to get the profiles of the nearby users, which is get profiles. It takes user token as input and the count. The count is the count of the profiles which the user want to get. Then as the user swipe left or right a profile, there will be an API that the client side Tinder application will be calling to actually like or dislike the user. So we can say that API is rate profiles. It takes user token and its profiles, and it also takes profiles rating. And this profiles rating will not be just for a single profile. There's no need to call this API for every swipe left or right. What we would do when the user is swiping left or right, we will be storing that information, and then once we have, let's say, 10 swipes or 15 swipes, then we will periodically be calling this API to actually like or unlike all those profiles in a batch call. Now there's one question for you guys. Do we need to provide the information about the dislike also to the Tinder application, or should we just use this to call only for those profiles which the user has liked? Let me know in the comments below what you guys think. Now let's discuss the overall architecture of the Tinder service. Before going into that, however, please, if you haven't subscribed to my channel, please subscribe to my channel. And if you haven't liked this video yet, then please like this video on the YouTube website. So the Tinder service will be comprising of several microservices. It has a routing or gateway service. So the Tinder client app will always be talking to the routing or the gateway service, and then it will be using this routing Tinder service to communicate with the other services or other microservices which the Tinder service exposes. We have analytics and monitoring service, we have chat service, we have swipe service, we have recommendation service, we have profile service, and we have user registration and SMS gateway and push notification service. So whenever a user creates a profile, the very first time the user goes to user registration service. Once the user account is validated, a profile is created in the profile service. The recommendation service is the service which actually shows all the nearby profiles to the user based on the search preferences that the user has provided to the Tinder service. Whenever a user swipe left or right, the swipes actually goes to the swipe service. And then once two users are matched, they can actually use the chat service to actually talk to each other. Now we will discuss the design of these individual services one by one. So the design of the routing or the gateway service will be similar to what we have discussed in our previous video of designing Uber service. So the Tinder client app will be communicating with the routing or gateway service either via WebSockets or via HTTP long pole. These both approaches have their pros and cons. I'm not going into details of those because I already have discussed them in my previous video in designing Uber. So please go and check it, which you can find here. Let's just assume that right now that Tinder application is using the WebSocket to communicate with the routing and gateway service. And this WebSocket connection is used to actually communicate with chat service, also sending swipes and also receiving different profiles of nearby users. Now we are going to discuss the design of the profile service and the user registration service together. I'm not going to discuss the design of the user registration service because it's almost the same as what we have discussed before in our previous video on designing WhatsApp service. So please go check out that video as well after watching this video if you would like to know how we will design a user registration service. Now let's discuss about the design of the profile service. The profile service will be storing the user information about all the user bio, the age, gender, and it will also be storing the user pictures as well. It will also include the user search preferences or parameters, which include the location of the user, the radius of the area to search, gender for searching, and other interests and properties, etc. It will store this information in a user table. The user table will be sharded by the user ID. So this is the format of the user table that we will have in the profile service. The user ID is the primary key, and of course this table will be sharded by the user ID itself, and it will have different information about the user like age, gender, maybe email address, phone number, etc. It also will have interest, etc. Now the main thing that to discuss here is that where should the user be storing his or her images. So the very first approach is that we store the images or pictures of the user within the same data store. Now in this approach there are two options we have. One option is that either in the same user table we add 5 more blob columns for storing the images in blob format. And the second approach is that apart from this user table we also have image table where we have user ID as a primary key along with some image ID, and we actually have a blob column there in that table, and then those image IDs are stored here in this table. The second approach is we store these images in a file system, and now we only store the path to the files here in this user table. And the third option we have is we store the images in a object storage service. Now we will discuss the pros and cons of all these approaches. Now first consider the first case where we store the images in the same data store. And as we have discussed, there are two approaches while we are storing the images in the same data store. Either we add 5 blob columns here for 5 images and we actually put the images there in those 5 columns, or we have a separate image table and we actually add images in the blob column there in the image table, but then we store the primary keys of those images from that table here in this bucket. Of course, when we are storing the images in the second bucket, then in order to get the images for the user we would require 2 lookups. The first lookup would be to the user table to get the primary keys for the user images, and then we have to then perform a lookup on the image bucket as well. And of course this user bucket and the image bucket, they both of them will be sharded by the user ID. So on the same partition the user information along with the user images will be stored. So now if we see the pros of this approach, we will see that it is very convenient and easy to implement, and it gives us flexibility. It enables us to add, remove or update images within a transaction. The replication to secondary replicas will be handled automatically by the data store itself. We don't need to worry about orphaned entries here in this approach because there won't be any orphaned files or images dangling around as compared to other approaches that we will discuss later. There will be a single security model that will be applicable to both the user data and the user images. And also the backup of the data store encompasses the whole data set, that is the user information along with the user images. However, the main issue or the main negative point about this approach is the scalability. First of all, taking backups for these data store will now take a large amount of time because the database is very large due to large blob images in it. In an ideal world where the processing power, bandwidth and storage are infinite, everyone would store images in the data store. Unfortunately, we don't live in an ideal world and databases are not perfect. Running nightly backups on a large database, which also includes millions of images, is very, very, very expensive. Running them on petabyte or even exabyte data is almost impossible, especially if you are dealing with relational databases. Also, you need to understand that images are binary blobs and they are opaque data. You cannot do anything with it in the database except read it or update it or delete it. Both reading and writing in that case involves disk I/O. You are not going to be using these images for indexing, of course, and so as far as the database engine is concerned, a blob is not much of a use. If you are using relational database, the storing images would be prohibitive based on the scale you might be dealing with. With NoSQL such as MongoDB, etc., these limitations start going away. However, please note, under the hood, all databases, whether they are NoSQL databases or relational databases, they store the records in the form of blocks. If the image size is bigger than the block size, then it's totally possible that that image will be stored in multiple blocks. So now when you are reading a record, and if you are using the approach where you have embedded the images here in the same bucket, now if you are reading the user record, it means that you might need to go and read from multiple blocks in the disk. This affects not only reading of the records, but it also affects the writing of the records as well. Also, sending images to the customers or users require going through your application and database layer. The image first need to be read from the database, which involves reading the image blob from the disk of the database and putting it in the RAM by the database engine, and then copied over to the application's memory and then handed off to the kernel to be sent through the network socket. It's wasting lots of RAM and CPU cycles. Also note that depending on the implementation of the database, serving large blobs might affect the performance of other I/O operations on the database. And also it's important to note that when you are performing any writes in your distributed data store, even the writes first goes to the primary replica where it commits those writes in a commit log, and that commit log is then replicated to all the secondary replicas. And now if your commit involves large blobs, then the size of those commit logs will become bigger, and it means it will take more time to actually replicate those commit logs to other replicas, and then it will take more time for those replicas to store those big blobs in their disk and return a successful response back to the primary replica. Now let's discuss the second approach, in which we store the file in a file system, and then we only store the path to the files in this user table. This approach has certain advantages. First of all, the size of your database would be very small because it will not be storing any big image blobs, and so also the commit logs will also be very small, and it is way faster to commit any writes in this table because the size of the commit log will be very small. It is also way faster to directly serve the files to the socket when the images need to be sent to the Tinder client application. However, this approach also has some cons. First of all, if you are storing images in the file system, then you are responsible for taking the backups of those files to some other place as well. Also, now uploading a file or deleting a file cannot be done within a database transaction. So there is more probability of having dangling image files now, where you actually delete the file path from the database, but somehow deleting the file from the file system failed, and now you are with a dangling file which is not going to be deleted. Also, the file system might work for a small number of files, but as the number of users increases and as the number of images uploaded by the users increases and it reaches to millions and billions, that even the file system becomes slower. And then you need to come up with a sharding story for your file system as well. Also, if a machine has millions or billions of files in the file system, then reading a file from millions and billions of files become way slower, because now reading of the file involves multiple disk IOs to retrieve the file handle that points to the location of the file on the disk. The reason being that the file system in that case will not be keeping the information of the directory and its metadata information, example inode data in Linux and other Unix-like operating systems, in RAM, as in that case an enormous amount of metadata is generated on the storage tier due to namespace directories and file inodes. Also, some file systems limit the number of files stored within a single directory or folder, which results in a large number of directories with multiple layers of large number of subdirectories. This again affects the read performance of the file system. The third option is to store the image files in a remote object storage like X3, etc., with their URI information stored in the data store. The remote object storage in that case will be responsible for making sure that the images are durable. In this video, we are not going to discuss the internal design of the object storage service itself. Maybe in a future video, I will discuss the design of object storage service. However, here you need to just understand that in an object storage service, we store different files or images or pictures or videos in the form of objects. From a user perspective, if you want to store a large number of objects like images or videos, etc., then an object storage service is a very good option. The file storage or the file system may potentially scale up to millions of files, but if you are talking about more than millions and billions of files, then storing them in object storage service is a viable option. It also integrates well with the caching services like CDN as compared to the first approach. I didn't mention, but the file system approach also deals very well with the CDN caching. I think the main advantage that we get by using object storage service is that, first of all, it's way scalable as compared to the first two approaches. And then the second thing that we get is we don't have to worry about the durability of the images or pictures, because object storage service will be handling that. However, please note, in both the file system and object storage service approach, you need to make sure that there are no dangling or zombie files that are present in the file system or the object storage service. So what it means that you need to make sure that the database always has up-to-date information about the files that are uploaded to the file system or the object storage service. And you have a reliable mechanism to deleting these files from the object storage service and file system, which should not cause any database integrity to be compromised. In any way, the most important thing is that you never want to serve the images from your database directly. Images should be up in the CDN. Often the CDN will call your web server to get the images for the first time. But after that, your images should really be served by the CDN. So this is the design of the profile service. We will have 3 or more application servers in the profile service. Of course, as the load on the profile service will increase, we can increase these stateless application servers as well. They will be talking to the data store through the cache, which is a distributed global cache. Now, if we are storing the images in the image storage, then of course there will be a separate image storage service. Otherwise, if we are storing the images in the same data store as we have here, then it will not exist in that case. And of course, these application servers are behind load balancer. Now we are going to discuss the design of the swipe service. The swipe service receives all the swipe information from the Tinder client app. The Tinder client app does not send the swipe information for every swipe left or right, because if we do that, it will put a lot of pressure on our backend. So what the client app does is that whenever a user is either swiping left or right different profiles, we actually keep track of all that information, and then we only send this information periodically to the swipe service. Let's say after every 10 swipes or 15 swipes or 20 swipes, we actually send that swipe information to the swipe service. This is the overall design of the swipe service. So whenever a user swipe left or swipe right to either unlike or like a user profile, the Tinder client app actually store those information, and then it periodically send the batch of those swipes to the swipe service. The swipe service itself consists of different application servers. There will be 3 or more application servers. I have a question for you. Can you guys tell me in the comment below why we need at least 3 application servers? So when the swipe API comes to one of the application server, it actually goes and check in the data store whether the swipe information is stored there or not. This is the schema of that table, where we have the primary key is a user ID 1 and user ID 2. So if a user A likes user B, then user ID 1 will always be the user ID of the user, which is in alphabetical order less than the user ID of the second user. So the app server will check whether there's already record exists here or not. If the record does not exist because user A just like user B and there was no record before, it will create the record here, and it will also set here user ID liked boolean equal to true. Now at some point in time in the future, when user B likes user A, then the call will come here in one of the app server, and the app server will check whether this information exists in the data store, and it will exist. In that case, it will update this record there, and it will also send a message to this push notification service to notify both the users that now they can initiate chat messages with each other. And now I have a couple of questions for you guys. First of all, let me know what do you guys think? Should we only store the like swipes in this table, or do you think we should also store the unlike swipes as well? That's the first question. The second question is, what do you think, what would be the suitable time we should keep the swipe information in this data store? Let's suppose user A liked user B, but for the last 1 year, the user B hasn't liked user A. Should we still keep this information in the data store, or do you think we can delete those swipes which are partial swipes and they are older than a certain threshold, like a month or 2 months or a year, for example? Let me know in the comment below what do you guys think. Now let's discuss the design of the recommendation service. Recommendation service is responsible for showing profiles of nearby users to the user based on his or her preferences that he or she has set. So the recommendation service can also be considered as a search service, because at the end what it's doing, it's searching for some other user profiles based on a user search preferences and then returning those results to that user. So there are two types of preferences that the user specify for the profile searching. The first set of preferences are called hard preferences. These hard preferences include the distance from the user, the age range, the gender orientation. These preferences are called hard preferences because if the user has specified that I would like to get the profiles of other users which are within the 50 miles radius, then the service should not show the user profiles of the users which are more than 50 miles away from the user. Or for example, if a user has specified that I'm only interested in the profiles of the people which are in the age range from 30 to 40 years of age, then the Tinder service should not be showing the profiles of the users to that user outside of that age range. And same applies for the gender orientation. And that's the reason these preferences are called hard preferences. Then the second type or the second category of the preferences are soft preferences. The soft preferences include those criteria which does not need to be actually met. For example, the interests. So if the user has specified that I'm interested in meeting people who also likes watching, let's say, football, or who likes watching movies, or who likes surfing, etc. So these preferences are still soft preferences, they are not hard preferences. The soft preferences also includes activities. So yeah, if someone likes playing video games and he like to meet other people who also like to play video games, or career path. So someone specified that I'm a lawyer and I would like to meet other lawyers as well, for example. So these are all soft preferences. They can be used to actually rank the user profiles that need to be shown to the user, but they cannot be used to actually exclude some profiles to be shown to the user. So again, the hard preferences are used to actually filter in or filter out the set of profiles that need to be shown to the user, while the soft preferences are only used to rank the profiles which need to be shown to the user. So the recommendation service use both the hard preferences and the soft preferences to recommend profiles to a user. After finalizing the list of profiles to be filtered in or filtered out based on the hard preferences, the recommendation service use the soft preferences to rank those profiles and then show them to the user. The goal of the recommendation service is to identify those profiles which a user is likely to swipe right. There is one more important property that is used by the Tinder recommendation service to rank the users, and it is how much active a user is. The more active a user is, the user profile is ranked higher and is shown more to other users. Now we will design the recommendation service based on these preferences. The recommendation service takes a subset of user data from the profile service and store it in its own data store. This data store will be geo-sharded. That is sharded by the geospatial location of the users. We have already discussed one mechanism of geo-sharding in our previous video on designing Uber. You can watch that video here. The other approach that we can also use to geo-shard a data store is using Google S2 library. Now, as compared to the size of the grid that we were using in Uber service, we can have grids of bigger size here in Tinder service. So the geoshard size can be bigger. Since the number of updates happening in each geoshard will be way less as compared to the number of updates that were happening in the driver location service in the Uber system design. The ideal size of the grid can be derived from the maximum distance we would support our users to specify in his or her search preferences. In this way, we only have to search in the grid in which user is present or the 8 other grids surrounding that grid. Also, instead of using the approach that we use in Uber service to generate the shard ID, we can use Google S2 library to generate a shard ID here. We can also think about using chord trees here as well, since the updates are not happening that often. And it's totally possible that some grids might have more profiles as compared to other grids. So we could think about dynamically sizing the grids, and then using a chord tree is a good approach. It is also doable now because here the updates are much less frequent as compared to the driver location service in the Uber system. Also, if you see the usage pattern of the users in countries which are at the opposite ends of the globe, for example USA or India, you might see that the time of the day when there's a peak load in India, at that time the load at the US may not be that much, and so on. So now in that case, if we map these geoshards into different machines, then we will see that half of the time the machines having geoshards of India will be at peak load, but then the remaining half of the time they will be underutilized. And same as the machines on which we have US geoshards, they will be performing at peak load at some of the time, but then other half of the time they will have very little load. So what we could do in that case, in order to minimize cost, we can map all those geoshards of India and US on the same physical nodes. So the compute and network resources are properly utilized throughout the day. However, please note, this is not possible in all the cases because there are certain countries which have regulations that for the users or the data of the users for those countries should not reside outside of those countries. For example, in EU, there is a regulation that the data for all the users in EU or European Union should be stored in the European Union region and should not be stored in servers which are outside the EU. Also, figuring out an optimal solution for mapping the geoshards to a physical nodes, it's a NP-hard problem. Most time, a random distribution serves the purpose quite good. This is the database schema used by the recommendation service. So it has a user profile bucket. The primary keys, you can say, the user ID, but of course we have the secondary keys on current grid and last login time, etc. And this table will be sharded by the grid ID or the current grid ID. So the design of the service would be almost similar to driver location service that we have discussed in designing Uber. The interest here will be a JSON string which includes all the different interests and activities that the user has specified. Tinder uses the Elasticsearch with multiple Lucene indices on the properties of feature set in which a user is interested. Also, the data set is geoshard. Now consider the case when the user calls get profile API to retrieve the list of nearby user profiles based on his or her search preferences. This query goes to the Elasticsearch geoshards near the user and the results are returned. Let's suppose the number of profiles returned in the results are around 50. Once the user has gone through all those 50 profiles, he will call the get profile API again. The API will go again to the geoshards near the user and will return again the results. Please note, however, it will be a very bad user experience if we return the same list of profiles again to the user. So please let me know in the comments below, what do you think? What would be the best way to actually do not send the same set of profiles to the user again and again? I think it's pretty obvious that running this query on the data store again and again, where we are querying some set of profiles and then we are filtering out those profiles based on the criteria that user have already seen them using some mechanism. Running these queries will be very, very expensive. And what it means that now if a user is calling get profile, then there's a lot of work that needs to be done within those get profile API call, and which then results in a large time taken by this API. And this will be a bad experience for the user now, because the user will be now waiting for the get profile API to return. As we have discussed in our non-functional requirement, that we would like the latency to actually get the profiles to be as minimal as possible. So it means we need some mechanism to cache those results in advance. So whenever the user calls the get profile API, we just return the cache results. And then asynchronously calculate the next set of results in that case. So we will be using an approach where we will be calculating these search results ahead of time, and we will be storing them for the user ahead of time. We will store them in a table, user search result. The schema of the table is as follows, where we have primary key, which is a user ID, then we have the last login time, and then we have a search results, which will be a JSON string containing the list of all the profiles that needs to be shown to the user. And of course we have some other columns in this table to make sure that the results of this the search results are not duplicate, or we are not sending the same search results to the user. I will let you comment what you think what would be those columns here. This table will be shared by the user ID itself. So you can imagine now in the recommendation service we have two different types of data set. Some are the geo-shard data set on which we run the search queries, and we then store the result of those search queries in a separate data set which is shared by the user ID. And so now we will be running background jobs periodically that will be running the search queries on the geo-shard data set, and will be storing those search results here. In order to optimize those search queries and also not to have extra load on the search data set, we can always cache the results of those queries and then use them to actually calculate the search results from multiple users in a batch. And also, if you don't want get profile API to always hit our database, you can also put a cache in front of the database. Please pause the video here and let me know what do you think, what would be the best read-write policy for that cache, and what would be the preferable eviction policy for that cache. If you have seen my previous video on designing a distributed cache, which you can find here, I have discussed different read-write policies on a distributed cache, and I also have discussed different eviction policies. In our case, in the Tinder service, in the recommendation service here, we will be using read ahead write policy. So what we are doing now in that case, we are not populating the cache when get profile API comes. We will be populating the cache ahead of time, so that when the get profile API comes, we can directly serve that API through the cache without going to the data store. And now, as far as the eviction policy is concerned, what do you guys think? What would be the eviction policy we would use? If you say least recently used, the answer is wrong. We will not be using least recently used, but we will be using most recently used, because the thing is that once we have returned the profile results from the cache to the user, we don't need those profiles in cache anymore. So we can always then discard those profiles from the cache in order to make room for other profiles information to be stored in the cache. So this is the design of the recommendation service. You can see here we have some stateless application servers, we have data store which will be geo-shard of course, and then we have distributed cache, geo-shard as well in that case. There will be some search agents, and then of course we have some distributed queue. So usually what happens now, that whenever a get profile API comes and we return the results from here, from the cache to the caller, at that time we also check whether there are enough results still stored in the cache that can be returned back again when the next time get profile API comes for the same user. If not, then we add that user here in this queue, and then there are search agents which are listening to that queue, and once they find a user, they actually run a query. They actually run the search for that user and then store the results again in the cache and the data store. So these search engines, while they are performing a search, they can actually use different techniques to rank the profiles for each user. These techniques can include different machine learning techniques as well. Machine learning algorithms and recommendation systems can be usually classified into two categories. The first is content based and the second is collaborative filtering methods. Modern recommendation systems uses both the approaches, and so as our recommendation service here as well. The content-based methods are based on the similarity of item attributes, and collaborative methods calculate similarity from the interactions. For example, in our case, the user swipes. However, going deeper into these machine learning algorithms would be a topic for a different day. So I'm going to stop the video here. I'm not going to discuss the design of the chat service. If you are interested in the design of chat service, please check my previous video on designing WhatsApp service that you can find here. I'm also not going to discuss the design of push notification service or the SMS gateway service. These I have already discussed in my previous video in designing WhatsApp service. So please go and check that video for more information about it. So let me know in the comments below whether you like my video or not, and if you have find this video useful, please do comment, and also please do like this video on the YouTube website, and also please do subscribe to my channel and click the bell notification icon. I will be uploading more and more videos on different system design of different important distributed systems and services, including, let's say, Netflix, Instagram, object storage, cloud storage, etc. And also let me know in the comments below if you would like me to make videos on certain topic, and I will also add those requests into the backlog of the different topics that I have in mind for which I will be making videos in future. Thank you and take care.